The object humans eventually named the Milky Way exists independently of language, culture, or interpretation. It is a physical structure with specific geometry, mass distribution, radiation sources, and optical consequences imposed by the position of the observer. From an astrophysical standpoint, it is a barred spiral galaxy approximately 100,000 light-years in diameter, containing on the order of a few hundred billion stars, large quantities of interstellar gas and dust, and a dominant dark matter halo extending far beyond the visible disk. The Sun is embedded within this system, orbiting the galactic center at a distance of roughly 26,000 light-years, moving through the disk with a period of about 230 million years. This interior vantage point determines everything about how the galaxy appears in the night sky. Unlike external galaxies, which are seen as discrete objects against a dark background, the Milky Way is not observed as a single bounded shape. Instead, it surrounds the observer. Its light reaches the eye from all directions along the galactic plane, creating a continuous distribution of unresolved stellar emission rather than a localized source. The appearance of a luminous band across the sky is therefore a geometric consequence of residing inside a flattened stellar disk. When the line of sight runs along the plane of that disk, the column density of stars increases dramatically. Each individual star may be faint and unresolved, but their combined emission adds together, producing a diffuse glow. When the line of sight tilts away from the plane, the path length through the stellar distribution shortens and the background becomes darker. This anisotropic distribution of light is the fundamental physical reason the Milky Way appears as a band rather than a uniform glow. The light forming this band is dominated by integrated starlight. At naked eye resolution, the vast majority of stars contributing to the Milky Way are not individually distinguishable. Their angular separations fall below the resolving power of the human eye, which under ideal, dark-adapted conditions is on the order of 1 arc-minute. Stars closer than this threshold blend together perceptually, their photons summed into a continuous luminance field. The resulting surface brightness depends on stellar density, luminosity function, and distance distribution. In the galactic plane, these factors align to maximize integrated brightness. In the halo and at high galactic latitudes, stellar density drops sharply and the glow fades. Superimposed on this luminous background are irregular dark structures that break the band into patches, lanes, and bifurcations. These are not absences of stars, but regions where interstellar dust absorbs and scatters visible light. Dust grains, typically submicron in size and composed of silicates, carbonaceous compounds, and ices, preferentially attenuate shorter wavelengths through extinction and reddening. Along long sight lines in the galactic plane, even modest dust densities accumulate into optically thick columns. The result is the appearance of dark rifts slicing through the bright band, particularly prominent toward the galactic center. These extinction lanes provide strong visual contrast and are among the most striking naked-eye features of the Milky Way under dark skies. From a physical perspective, these dust lanes trace the same spiral structure as the stars themselves. Molecular clouds, cold atomic gas, and dust are concentrated in spiral arms where star formation occurs. The Sun's location between major spiral arms further enhances contrast, allowing observers to look both along dense arms and across relatively clearer inter-arm regions. This spatial configuration creates the illusion of structure and texture in the Milky Way band, reinforcing the impression that it is a tangible object laid across the sky rather than a statistical projection of countless distant sources. The galactic plane itself is not aligned with Earth's equator or ecliptic. Its tilt causes the Milky Way to arc across the sky at different orientations depending on season and latitude. At mid-northern latitudes, it rises steeply from the horizon in summer and lies lower in winter. Near the equator, it forms a nearly vertical arc at certain times of year. In the southern hemisphere, the galactic center passes high overhead, producing an especially bright and structured appearance. These changes are purely geometric, driven by Earth's rotation and orbit, yet they give rise to a dynamic visual experience that encourages interpretation and naming. The Milky Way does not resemble a cloud because its brightness distribution is anisotropic and elongated rather than roughly circular. It does not resemble a cluster because clusters present localized concentrations with clear edges, whereas the Milky Way has no visible boundary. The eye instead perceives a continuous, extended feature with gradual intensity gradients. This morphology is precisely what one would expect from a disc-shaped stellar system viewed from within, where the longest sight lines lie in a single great circle across the celestial sphere. Human visual physiology plays a critical role in shaping this perception. Under low light conditions, vision transitions from photopic cone-dominated operation to scotopic rod-dominated operation. Rod cells are far more sensitive to light, but lack color discrimination and have lower spatial resolution. They are optimized for detecting faint, diffuse luminance rather than fine detail. The Milky Way's surface brightness falls squarely within the regime where rods dominate perception. As a result, the band appears pale, whitish, or faintly grey rather than colourful, even though it is composed of stars spanning a wide range of intrinsic colours. Contrast sensitivity under scotopic vision is also highly non-linear. The eye is more responsive to differences in brightness than to absolute brightness levels. This enhances the visibility of dust lanes as dark features against a luminous background and exaggerates the perception of texture within the Milky Way. Small variations in surface brightness, which would be difficult to detect in daylight, become salient at night. The brain, evolved to detect patterns and edges in low-contrast environments, readily organizes these variations into coherent shapes. Another critical factor is the absence of reference frames in the night sky. Unlike terrestrial scenes, the sky lacks depth cues such as parallax, occlusion, and familiar object sizes. The Milky Way therefore appears neither near nor far in any intuitive sense. Its scale is ambiguous. It can be perceived as a substance spread across the sky, a path overhead, or a boundary dividing regions of darkness. This perceptual ambiguity encourages metaphorical interpretation, but the underlying trigger is a well-defined physical signal interacting with a specific sensory system. The integration time of human vision further contributes to the effect. Rod cells effectively sum incoming photons over tens to hundreds of milliseconds, allowing extremely faint light to accumulate into a detectable signal. This temporal integration smooths fluctuations and reinforces the appearance of continuity. Individual stars blink and scintillate due to atmospheric turbulence, but the Milky Way band remains steady, reinforcing the impression of a persistent structure rather than a collection of points. Importantly, the Milky Way's visibility is highly sensitive to background sky brightness. Artificial lighting raises the sky's luminance, reducing contrast and overwhelming the faint, integrated starlight. Under such conditions, the band disappears entirely, leaving only isolated bright stars. This dependence explains why the Milky Way played such a prominent role in pre-industrial cultures, and why it is absent from the lived experience of many modern observers. Its cultural significance correlates directly with its physical detectability. From a scientific standpoint, nothing about the Milky Way's naked eye appearance is accidental. Its band-like form follows from disk geometry. Its brightness follows from stellar density and luminosity functions. Its dark lanes follow from interstellar dust physics. Its colorlessness follows from scotopic vision. Its capacity to inspire naming follows from the interaction between a complex but stable astrophysical signal and a perceptual system tuned to extract structure from low-light environments. Before it was called a river, a road, milk, smoke, ash, or a spine of the sky, it was already this object. A flattened, rotating stellar system observed from within, projected onto the celestial sphere as a luminous great circle, textured by dust and filtered through the physiology of the human eye. Every name that would later arise begins here, with this physical reality and this shared visual experience. Every human culture that developed under a natural night sky encountered the same large-scale visual structure because the observing platform was the same planet embedded in the same galactic environment. Earth orbits a star located inside a flattened stellar disk. This single geometric fact constrains the appearance of the night sky in a way that is independent of language, belief, or tradition. The consistency of the Milky Way's shape across cultures arises from the invariance of this geometry combined with the regular motions of Earth in space. The stellar system, known as the Milky Way, is not spherical. Its mass is distributed primarily in a thin disk with a scale height of only a few hundred light-years for the majority of its stars and interstellar matter. The Sun lies within this disk, offset slightly above the midplane, but close enough that sight lines along the plane pass through enormous path lengths of stellar material. From any point inside such a disk, the highest surface brightness will always occur along directions tangent to the disk plane. When projected onto the celestial sphere, those directions define a great circle. This is the band that appears in the sky. Because Earth's rotation axis is fixed relative to the stars on human timescales, and because the galactic plane has a fixed orientation relative to Earth's equator, the Milky Way traces a stable arc across the sky that repeats night after night. Its exact position changes with the time of night and the season, but its shape does not. This regularity is essential. A feature that drifts unpredictably or appears only rarely would not be named consistently. The Milky Way is persistent, structured, and predictable, making it a natural candidate for recognition and classification. Seasonal visibility follows directly from Earth's orbital motion around the Sun. As Earth moves along its orbit, the nighttime side of the planet faces different directions in space. This determines which regions of the galactic plane are visible at night and which are lost in solar glare. When the galactic center lies near the midnight meridian, the Milky Way appears brighter and more complex, because that direction intersects the densest stellar regions and the most prominent dust structures. When the galactic center lies near the Sun's position in the sky, only the outer, less luminous parts of the disk are visible at night, and the band appears fainter. This seasonal modulation is not subtle. At mid-latitudes in the northern hemisphere, the brightest portion of the Milky Way dominates summer nights, arching high across the sky, while winter nights show a dimmer, less textured band. In the southern hemisphere, the effect is even more pronounced because the galactic center passes nearly overhead at certain times of year. These predictable cycles mean that human observers repeatedly encountered the same structure under varying conditions, reinforcing its identity as a coherent object rather than a random accumulation of stars. Latitude further shapes the experience. The inclination of the galactic plane relative to Earth's equator means that observers at different latitudes see the Milky Way at different maximum elevations. Near the equator, the band can span from horizon to horizon, rising nearly vertically and passing through the zenith. At higher latitudes, it remains lower in the sky, compressed toward one horizon or the other. Despite these differences, the underlying shape remains recognizable. The same luminous band is present everywhere on Earth, where the night sky is dark enough, only tilted, stretched, or truncated by the horizon. This universality is critical. Unlike constellations, which depend heavily on cultural choices about which stars to group together, the Milky Way is imposed by physics. It is not constructed by drawing imaginary lines between points. It is an extended luminance feature that exists regardless of how one chooses to interpret individual stars. Even cultures with radically different symbolic systems encountered the same basic form, a continuous irregular band dividing the sky into two hemispheres of differing star density. Agricultural societies in particular were uniquely positioned to notice and repeatedly engage with this structure. Agriculture demands long-term attention to seasonal cycles, celestial timing, and environmental regularity. Communities tied to planting and harvesting schedules spent nights outdoors, often far from artificial light sources, observing the sky as part of practical life rather than leisure. The same attentiveness used to track the sun's path or the phases of the moon naturally extended to prominent nocturnal features. The Milky Way's seasonal changes correlate loosely with climatic cycles in many regions. Its brightest visibility often coincides with warmer months when outdoor activity increases. Over generations, this repeated association between the band's position and seasonal rhythms would have reinforced its salience. It became part of the sky's background structure, as reliable as the horizon itself. Nomadic and pastoral societies also encountered the Milky Way frequently, but agricultural settlements added permanence. Fixed observation sites allow long-term pattern recognition, a structure that returns year after year in the same orientation relative to the landscape becomes embedded in cultural memory. Stone structures, ritual sites, and early architectural alignments sometimes incorporated the Milky Way's orientation, further anchoring its form in collective experience. Pre-industrial dark skies are an essential part of this explanation. The Milky Way's surface brightness is low. Even under pristine conditions, it is only marginally brighter than the natural night sky background produced by airglow, zodiacal light, and scattered starlight. Artificial illumination dramatically increases sky brightness, reducing contrast and erasing diffuse features first. The Milky Way is therefore one of the earliest casualties of light pollution. Before the widespread use of artificial lighting, night skies routinely reached surface brightness levels near the natural minimum set by atmospheric and interplanetary processes. Under such conditions, the Milky Way is not subtle. It is a dominant feature of the sky, visible even to inexperienced observers. Dust lanes, bifurcations, and brightness gradients are readily apparent. The band can cast faint shadows under exceptional conditions, an effect documented in multiple historical sources. In these environments, the Milky Way was not something one had to search for. It was always present. Its absence on cloudy nights or during certain seasons would have been as noticeable as its presence. This constancy made it a reference feature against which other celestial motions were perceived. Planets wandered across it. The moon crossed and obscured it. Comets emerged from it and disappeared back into it. These interactions further reinforced its identity as a distinct structure. Human visual perception also benefits from repeated exposure. Pattern recognition improves with familiarity. A child growing up under dark skies learns the Milky Way's shape implicitly, without instruction. Over time, subtle features become obvious. Bright star clouds, dark rifts, and changes in thickness are all learned through passive observation. This learning process operates similarly across cultures because the underlying stimulus is the same. The shape itself invites segmentation. The Milky Way is not uniform along its length. Certain regions bulge, others thin. Dark lanes split it into parallel streams in some areas. These variations provide natural anchors for naming and interpretation. Cultures may disagree on what the band represents, but they rarely disagree on where it is or what its general outline looks like. The fact that nearly every culture perceived a path, river, or substance, rather than a collection of points, is a direct consequence of how the galaxy's light reaches the eye. Integrated starlight produces a continuous signal, while individual stars within the band are visually subordinated to the glow. This perceptual dominance of the whole over the parts is consistent across observers with normal vision, regardless of training. Earth's atmosphere further homogenizes the experience. Atmospheric scattering blurs faint point sources and smooths brightness gradients. While this degrades astronomical resolution, it enhances the visibility of extended low-contrast features. The Milky Way benefits from this effect. Its band-like appearance is reinforced by the same atmospheric processes that limit telescopic clarity. The long-term stability of the Milky Way's appearance is another key factor. On human timescales, the galaxy's structure does not change. Stellar motions, spiral arm evolution, and dust redistribution occur over millions of years. As a result, the band observed by early humans tens of thousands of years ago would have been indistinguishable from the one seen by classical civilizations and medieval astronomers. This temporal continuity allows naming conventions to persist and spread. Cultural exchange amplified this stability. As societies interacted through trade, migration, and conquest, names and interpretations of the Milky Way were shared and adapted. However, this transmission did not create the shape itself. It only layered meaning onto a form that was already universally recognized. Even isolated cultures with minimal contact developed their own names for the same structure, confirming that the stimulus alone was sufficient. In summary, every culture saw the same shape because the conditions of observation were effectively identical at the relevant scale. A planet rotating and orbiting inside a disk galaxy under dark skies, viewed with human eyes, will always produce a luminous band across the sky. Differences in latitude, season, and environment modulate brightness and orientation, but not the fundamental morphology. The Milky Way's universality is therefore not a coincidence of mythology, but a consequence of astrophysics, planetary motion, and human perception acting together. The Greek term galaxias did not emerge from metaphorical excess or poetic ornament. It arose from a specific visual problem: how to describe a persistent, diffuse, pale structure spanning the night sky when observed with the unaided human eye. The word derives from gala, meaning milk, and its application to the sky reflects a precise perceptual judgment grounded in optical appearance rather than mythology. To understand why this term was selected and why it proved so durable, it is necessary to examine how unresolved starlight behaves, how the human visual system interprets that light, and how ancient Greek observational practices favoured descriptive accuracy over narrative elaboration. In classical Greek usage, gala referred to a substance characterized by whiteness, opacity, and smooth continuity. Milk is not transparent, nor is it granular when viewed at normal scales. It reflects and scatters light in a way that produces a uniform pale luminance, with subtle variations but no sharp edges. These properties align closely with the naked eye appearance of the luminous band later called the Milky Way. Under dark skies, the band is not sharply bounded, not composed of visible points at a distance, and not strongly coloured. It is diffuse, softly textured, and light-toned against a darker background. The analogy is visual and material, not symbolic. From an optical standpoint, the Milky Way's pale appearance is a direct consequence of unresolved starlight combined with human scotopic vision. The vast majority of stars contributing to the band lie below the eye's resolution threshold. Their angular separations are too small for individual discrimination, and their photons are integrated into a continuous surface brightness. This integration produces a luminance field with low spatial frequency content, smooth changes over large angular scales, rather than high-frequency point sources. Milk exhibits a similar optical behavior. It is a colloidal suspension that scatters light multiple times within the medium, erasing directional information and producing a uniform appearance. In astrophysical terms, the Milky Way's surface brightness arises from the summed emission of stars spanning a wide luminosity range. While intrinsically bright stars contribute disproportionately, their individual signatures are lost in the aggregate. The resulting spectral energy distribution is weighted toward the combined output of numerous cooler stars, which emit strongly in the visible but without intense color saturation. Interstellar dust further attenuates and reddens the light, preferentially removing blue wavelengths and flattening color contrasts. The net effect is a pale, slightly warm-toned glow that lacks vivid chromatic features. This visual outcome closely matches the perceptual category associated with milk. Greek observers did not possess a theoretical framework for stellar populations or dust extinction, but they did possess acute observational vocabulary. Greek natural philosophy emphasized classification based on appearance and behavior. Terms were chosen to describe what was seen, not what was imagined. The decision to label the band as galaxias reflects this empirical impulse. Milk was a familiar substance with well-defined visual properties. It provided a ready-made descriptor for a celestial feature that shared those properties when viewed under similar lighting conditions. It is important to note what the term does not imply. Milk is not luminous in itself. It reflects ambient light. The Milky Way, by contrast, emits light. However, under low light conditions, the human visual system does not distinguish emission from reflection in extended sources. Both appear as diffuse luminance fields. The analogy therefore operates at the level of perception, not physical mechanism. This distinction would not have been meaningful or necessary in ancient observational contexts. The choice of milky also distinguishes the Greek approach from cultures that emphasized linearity or motion in their naming. Milk suggests a substance spread across space rather than a path or boundary. This aligns with how the band appears when traced across the sky, not as a narrow line, but as a broad, irregular swath with variable thickness. Greek descriptions often note this width and unevenness, indicating sustained attention to the feature's morphology. Optical scattering plays a central role in reinforcing this appearance. In the atmosphere, Rayleigh scattering preferentially affects shorter wavelengths, contributing to the night sky background. Within the galaxy, scattering and absorption by dust redistribute starlight, smoothing intensity gradients and enhancing diffuse components. These processes reduce contrast at small scales and emphasize large-scale brightness patterns. Milk, as a scattering medium, exhibits analogous behavior. Light entering milk undergoes multiple scattering events, losing directional coherence and emerging as a uniform glow. The perceptual similarity is strong enough to justify the analogy without invoking symbolism. The durability of the term galaxias is partly due to its accuracy. When Galileo later resolved the Milky Way into countless faint stars using a telescope, he demonstrated that the band's diffuse appearance was an emergent property of unresolved sources. This discovery did not invalidate the name. On the contrary, it explained why the name worked. The band looks milky because it is composed of innumerable small light sources whose individual identities are lost to the eye. The original descriptor remained compatible with the new understanding. Linguistically, the Greek term proved highly transmissible. Latin authors adopted it as via lactea, translating the meaning rather than preserving the phonetics. This translation preserved the visual analogy exactly. Subsequent European languages inherited either the Latin phrase or its direct descendants. English, Milky Way, French Voie lactée, Italian Via Lattea, and Spanish Via Lactea all encode the same perceptual judgment. The persistence of this descriptor across languages and centuries reflects its continued relevance to naked eye observation. In modern astronomy, the term survives with minimal modification. While astrophysical discourse distinguishes between the Milky Way as a galaxy and the Milky Band as an observational phenomenon, the name bridges both concepts. It refers simultaneously to the physical object and its visual manifestation. This dual usage is unusual, but historically grounded. The galaxy was named before its nature was understood, and the name was descriptive enough to remain valid after that understanding emerged. The survival of the term also illustrates a broader principle in scientific nomenclature. Names rooted in stable observational features tend to persist even as theoretical frameworks change. The Milky Way's appearance has not changed on human timescales. As long as observers on Earth look out from within a disk galaxy under dark skies, the band will retain its milky aspect. The name remains functionally descriptive. Greek astronomical texts rarely treat the Milky Way as a mythological object in their technical discussions. While myths existed in parallel cultural contexts, observational astronomy maintained a separate register. Descriptions focused on position, extent, and appearance. The term galaxias fits squarely within this register. It communicates information about brightness, texture, and continuity without invoking narrative elements. This pragmatic orientation contributed to its adoption and longevity. From a cognitive perspective, the analogy leverages common sensory experience. Milk was ubiquitous in ancient Greek society. Its visual properties were well known. By applying this familiar reference to a celestial phenomenon, observers could communicate effectively about something otherwise abstract and distant. The analogy reduced cognitive load by mapping an unfamiliar large-scale structure onto a known material category. This mapping did not distort the observation, it clarified it. Modern astrophysics has added layers of meaning to the Milky Way without erasing the original descriptor. We now understand the galaxy's spiral structure, stellar populations, kinematics, and dark matter halo. Yet none of these invalidate the visual impression that first prompted the name. If anything, they reinforce it. The integrated light of billions of stars, filtered by dust and perceived by the human eye, produces exactly the kind of diffuse luminance field that the term galaxias captures. The Greek choice of milk therefore stands as an example of effective early scientific naming. It is grounded in direct observation, aligned with perceptual reality, and robust against later theoretical revision. Its survival into modern astronomical language is not an accident of tradition, but a consequence of its continued descriptive accuracy. Roman astronomy did not emerge as an independent observational tradition detached from what came before it. Instead, it developed as a deliberate continuation of Greek astronomical language, geometry, and classification. This continuity is especially clear in the Roman handling of the Milky Way, where the Greek descriptive framework was not replaced, but translated, preserved, and embedded into a broader system of Latin scientific discourse. The Roman term Via Lactea is not a reinvention, it is an explicit linguistic transmission that signals respect for Greek observational authority, and an understanding that certain celestial features did not require conceptual revision. By the time Roman scholars began to engage systematically with astronomy, Greek observational astronomy had already reached a mature stage. Star catalogues, geometric models of celestial motion, and descriptive terminology were well established. Greek astronomers had mapped the sky using coordinate systems tied to the celestial sphere, identified fixed stars, tracked planetary motion, and described extended features such as the Milky Way with consistent language. Roman intellectual culture, particularly in technical domains, prioritized synthesis and standardization over novelty. Astronomy was treated as a body of inherited knowledge to be preserved, taught, and applied rather than reinterpreted symbolically. The Latin phrase Via Lactea, meaning the Milky Road, is a direct semantic translation of the Greek galaxias. The choice to translate meaning rather than invent a new descriptor is significant. Roman scholars recognized that the Greek term already captured the essential visual properties of the phenomenon. The luminous band across the sky observed from Earth had not changed, and Roman observers saw the same structure under the same dark skies. There was no empirical motivation to rename it. Instead, the goal was linguistic accessibility within the Latin-speaking world. This approach reflects a broader Roman attitude toward Greek scientific terminology. In disciplines such as geometry, medicine, and astronomy, Greek terms were often retained outright or carefully translated to preserve their conceptual content. The Milky Way, now referred to as the Milky Way, was treated as a fixed astronomical object whose descriptive identity was already established. Renaming it would have introduced ambiguity rather than clarity. Roman scholars also relied heavily on Greek sky maps and coordinate systems. These maps were not symbolic illustrations, but practical tools for navigation, calendar regulation, and philosophical inquiry. The positions of stars, the orientation of the ecliptic, and the path of the Milky Way were encoded in a geometric framework that linked observation to mathematical description. Altering terminology without altering the underlying geometry would have disrupted this framework. Preservation ensured continuity of meaning across generations and regions. The Roman educational system further reinforced this continuity. Astronomy was taught as part of a broader curriculum that included geometry and natural philosophy. Texts by Greek authors were translated, commented upon, and disseminated throughout the Roman world. Students learned to recognize the Milky Way as a specific feature of the celestial sphere, defined by its position relative to the zodiac and fixed stars. The name via Lactea functioned as a label for a known region of the sky, not as a narrative or mythological construct. Early Roman attempts to systematize celestial nomenclature focused on classification rather than reinterpretation. The sky was divided into recognizable components: fixed stars, wandering stars, constellations, circles of the sphere, and extended features. Names were chosen to facilitate reference and calculation. The Milky Way occupied a unique category. It was neither a constellation, nor a planet, nor a single object. It was an extended, luminous region, requiring a descriptor that conveyed continuity and breadth. The existing Greek analogy fulfilled this requirement efficiently. Roman authors such as Pliny the Elder discussed the Milky Way in naturalistic terms, emphasizing its appearance and location rather than attributing new symbolic meaning. While mythological explanations circulated in popular culture, technical discussions treated the band as a physical feature of the heavens. This separation between cultural myth and scientific description allowed the name to remain stable, even as interpretations varied in non-technical contexts. The Roman emphasis on order and taxonomy also played a role. Naming was seen as a means of imposing structure on the natural world. A stable name implied a stable object. The Milky Way's consistency in appearance supported this view, unlike comets or novae, which appeared unpredictably and demanded new descriptive language. The Milky Way was always present. Its predictability aligned with Roman ideals of cosmic order. The translation of galaxias into Via Lactea also demonstrates an important linguistic principle. Latin did not simply borrow Greek words wholesale in all cases. Where possible, it rendered them into Latin equivalents that preserved descriptive content. This made scientific texts more accessible while maintaining conceptual fidelity. The Milky analogy survived intact because it remained visually accurate under Roman observation conditions. As Roman influence expanded across Europe, North Africa, and parts of the Near East, Latin astronomical terminology spread with it. The Milky Way's name became embedded in legal calendars, agricultural guides, and educational texts. Its presence in these practical documents further reinforced its status as a recognized and stable celestial feature. Over time, the Latin term became the root for names in emerging Romance languages and influenced terminology beyond them. Importantly, Roman preservation of Greek sky maps ensured that positional knowledge associated with the Milky Way remained consistent. The band's relation to constellations and the ecliptic was recorded and transmitted with minimal alteration. This allowed later scholars to build upon existing data rather than reconstruct it. When medieval and early modern astronomers returned to classical sources, they encountered a coherent system in which the Milky Way's name and location were already standardized. The absence of renaming also reflects the lack of new observational insight at the naked eye level. Roman astronomy did not introduce instruments capable of resolving the Milky Way into stars. Without new data, there was no impetus to revise descriptive language. The band still appeared as a diffuse, pale structure. The inherited name continued to match the observation. Early efforts to systematize celestial nomenclature during the Roman period laid the groundwork for later scientific classification. By treating names as functional labels tied to observable properties, Roman scholars contributed to a tradition of descriptive stability. This tradition would later allow revolutionary discoveries to be integrated without linguistic chaos. When telescopes revealed the Milky Way's stellar nature, the name did not need to change. It already described the phenomenon at the scale of human perception. In this sense, Roman adoption of Greek terminology represents continuity rather than stagnation. It reflects an understanding that scientific language serves observation first. The Milky Way did not demand reinterpretation because its defining feature, a luminous band across the sky, remained unchanged. By preserving Greek descriptors and embedding them in Latin scholarship, Roman astronomy ensured that this feature retained a consistent identity across centuries. The result is a rare case of linguistic durability in science. From Greek galaxias to Latin Via Lactea and onward into modern languages, the name has remained anchored to the same visual reality. Roman scholars acted as custodians of this continuity, transmitting not only words, but a disciplined approach to celestial description. Their restraint in renaming reflects an early recognition that accurate observation, once properly named, does not require constant revision. Ancient Near Eastern interpretations of the Milky Way emerged from one of the earliest sustained traditions of systematic sky observation in human history. In Mesopotamia, astronomy developed not as speculative philosophy but as a practical, state-supported discipline tied to timekeeping, ritual regulation, and omen interpretation. The appearance of a persistent, luminous band across the sky therefore entered recorded knowledge as an observed structure with functional significance rather than as a purely symbolic image. What later cultures would call the Milky Way was already recognized in Mesopotamia as a linear feature embedded within an ordered celestial framework. Cuneiform sky tablets from Sumerian, Akkadian, Babylonian and Assyrian traditions reveal a strong emphasis on linearity in celestial description. The sky was not conceived as a random scatter of lights, but as a structured surface marked by paths, zones, and divisions. The ecliptic planetary paths and stellar groupings were described as roads or tracks along which celestial bodies moved. Within this conceptual system, a bright, continuous band cutting across the sky naturally lent itself to interpretation as a boundary or route. Mesopotamian astronomical texts often classify stars according to their relation to three major celestial ways: the way of Anu, the way of Enlil, and the way of Ea. These divisions correspond roughly to bands of declination across the sky, separating northern, equatorial, and southern regions. The Milky Way intersects these zones, sometimes aligning closely with their boundaries. This spatial coincidence reinforced its interpretation as a divider between celestial domains rather than as an isolated object. Unlike later Greek descriptions that emphasized texture and brightness, Mesopotamian records focus on position and continuity. The luminous band is treated as part of the sky's underlying structure, a feature that helps organize other celestial phenomena. In omen literature, references to bright or dark regions of the sky often assume the presence of a known background pattern against which unusual events are measured. The Milky Way provided such a background, a stable reference line that rarely changed and therefore carried interpretive weight. The concept of the sky as layered or partitioned was central to early Near Eastern cosmology. The heavens were not infinite space, but a structured canopy above the earth, governed by divine order. Linear celestial features fit naturally into this world view. A band dividing the sky could be associated with separation between realms, routes of divine travel, or limits beyond which certain influences did not pass. These interpretations were not arbitrary inventions. They arose from repeated observation of the same geometric feature under consistent conditions. Ritual calendars in Mesopotamia depended heavily on predictable celestial cycles. Months were tied to lunar phases, years to solar motion, and longer cycles to planetary patterns. Fixed stars and extended sky features provided additional anchors for timing. The Milky Way's orientation relative to the horizon changes with the seasons, making it a useful indicator of time progression. Its rising and setting points shift slowly over the year, offering coarse but reliable seasonal markers. In some ritual contexts, the Milky Way appears to have functioned as a delimiter for auspicious and inauspicious regions of the sky. Certain omens were interpreted differently depending on whether they occurred on one side of a celestial boundary or another. A continuous luminous band offered a natural dividing line that could be referenced consistently across observations. This role required stability, which the Milky Way provided due to its unchanging large-scale structure. Mesopotamian astronomical practice also involved long-term record-keeping. Observations were recorded over centuries, allowing patterns to be recognized and codified. The Milky Way's persistent presence would have been noted implicitly through its repeated appearance in the same relative position among the stars. Although individual texts may not elaborate on its nature, its inclusion in the conceptual background of the sky is evident from how other features are described in relation to it. The association of the Milky Way with paths reflects a broader cultural emphasis on roads and canals in Mesopotamian society. Linear infrastructure dominated the landscape, connecting cities, fields, and waterways. This environmental context shaped how celestial linearity was perceived. A luminous band stretching across the sky would naturally be understood in terms of routes or divisions, mirroring the organization of the terrestrial world. Importantly, these interpretations did not require mythic embellishment to be meaningful. The Milky Way's role as a boundary or path was operational. It helped structure the sky for purposes of observation, interpretation, and ritual timing. Mythological narratives, where they existed, coexisted with this functional understanding but did not replace it. The relationship between celestial bands and ritual calendars illustrates how astronomy and religion were intertwined without being confused. Rituals were scheduled according to celestial regularities because those regularities were reliable. The Milky Way's predictable orientation at different times of year made it part of the visual language through which time was read. Its presence reinforced the perception of cosmic order, a key principle in Near Eastern thought. Unlike point sources such as stars or planets, the Milky Way could not be associated with a single deity or omen. Its scale and continuity placed it in a different category. It functioned more like a structural element of the sky than an actor within it. This distinction may explain why it is less frequently personified in surviving texts than other celestial features. Its role was foundational rather than narrative. The durability of this interpretation is notable. Later cultures in the Near East inherited similar conceptions of the sky as divided into regions and paths. Even as languages and political systems changed, the underlying geometry of the sky remained the same. The Milky Way continued to appear as a luminous band intersecting the celestial sphere, and it continued to be interpreted within frameworks that emphasized order, boundary, and continuity. From a modern perspective, these early interpretations align closely with the physical reality of the galaxy's appearance. The Milky Way is indeed a planar structure, and its projection onto the sky creates a natural dividing line. Mesopotamian observers lacked the tools to explain why this was so, but their descriptive frameworks captured the essential geometry accurately. In summary, ancient Near Eastern interpretations of the Milky Way were shaped by systematic observation, practical timekeeping needs, and a cosmology that emphasized structure and order. Sky tablets encoded a world view in which linear features mattered because they organized experience. The Milky Way's role as a boundary or path was not a poetic invention, but a rational response to a persistent and visually dominant feature of the night sky. Its integration into ritual calendars reflects the deep connection between celestial regularity and human attempts to impose order on time, space, and society. Ancient Chinese astronomy developed as a long-term, state-supported observational science whose primary goals were calendrical regulation, positional accuracy, and the detection of subtle changes in the sky. Within this framework, the Milky Way was identified not as a diffuse substance or background glow, but as a structured divider with geometric and dynamical significance. The term, commonly translated as the celestial river, reflects a descriptive choice grounded in repeated measurement, careful sky partitioning, and an implicit understanding of large-scale motion rather than metaphorical flourish. Chinese astronomers worked within an observational tradition that emphasized continuity and precision over speculative explanation. Court astronomers maintained records spanning centuries, tracking stellar positions, planetary motions, eclipses, and transient events. The sky was divided into a dense network of asterisms rather than large pictorial constellations. Each star or small group of stars had a defined place within a coordinate-like system tied to the celestial equator and the lunar mansions. In this highly structured sky, the appearance of a broad, luminous band crossing many regions demanded classification as a major organizing feature. That feature is what modern astronomy identifies as the Milky Way. In Chinese astronomical texts, it is most often described as a river or stream separating distinct stellar territories. This description arises directly from its appearance when observed systematically over the year. The band is elongated, continuous, and uneven in width. It flows across the sky rather than remaining confined to a single area. Stars appear embedded within it, adjacent to it, or clearly separated from it, much like settlements along the banks of a river. The division imposed by this celestial river is not symbolic in origin, but positional. Chinese sky maps clearly distinguish stars north and south of the band. The Milky Way cuts through the celestial sphere at an oblique angle, intersecting numerous lunar mansions and passing between recognized star groups. Its presence creates a natural partition that simplifies description. Stars can be referenced by their relation to the river, much as terrestrial locations are described relative to waterways. This approach aligns with the broader Chinese cosmological emphasis on balance, structure, and flow. However, the descriptive choice of river is rooted first in observation. Rivers on Earth are long, continuous, directionally extended features that guide movement and separate regions. The Milky Way exhibits the same visual characteristics. It is not amorphous like a cloud, nor bounded like a cluster. It extends across the entire sky with gradual changes in thickness and brightness, and no clear endpoints. Early Chinese star catalogues demonstrate how this feature was integrated into positional astronomy. Stars were not grouped arbitrarily. Their coordinates relative to the celestial equator and to one another were carefully noted. The Milky Way's path provided a reference curve against which stellar positions could be contextualized. Its intersections with specific lunar mansions were recorded, allowing astronomers to track seasonal changes in its orientation relative to the horizon. These seasonal changes were particularly important for calendar regulation. As Earth orbits the Sun, different segments of the Milky Way dominate the night sky at different times of year. The rising and culmination of the brightest portions provided visual cues that complemented more precise lunar and solar measurements. The river's flow across the sky was therefore not static in experience, even though its structure was stable. This apparent motion reinforced the river analogy. From a kinematic perspective, the river metaphor aligns surprisingly well with modern understanding. While ancient Chinese astronomers had no concept of galactic rotation, they did observe that stars and stellar groups moved coherently across the sky due to Earth's rotation and precession. The Milky Way, as a fixed, large-scale structure, appeared as a channel through which these motions occurred. Planets crossed it, the moon obscured sections of it, comets emerged from and disappeared into it. These interactions suggested a medium or pathway rather than a static background. The river designation also reflects the prominence of dark dust lanes within the Milky Way. These lanes create the appearance of branching or splitting, similar to tributaries or divided currents. In regions near the galactic center, the band is visibly bifurcated, with dark rifts separating brighter streams. To an observer accustomed to reading landscapes and waterways, this structure would naturally evoke fluvial imagery. The analogy captures not only brightness, but internal structure. Chinese astronomical texts often describe the Milky Way as separating the sky into northern and southern domains with different symbolic and functional associations. This division is mirrored in the actual distribution of stellar density. The galactic plane hosts a higher concentration of stars, while regions farther from it are sparser. The river therefore marks a transition zone between crowded and less crowded stellar fields, a distinction that would have been evident to careful observers. The precision of Chinese observational astronomy ensured that this was not a casual impression. Records were compared across generations. Deviations were noted and investigated. The Milky Way's persistence as a dividing feature reinforced its classification as a fundamental component of the celestial framework. Its name encoded its role rather than its composition, which was unknown. Unlike cultures that emphasized mythological origin stories for the Milky Way, Chinese astronomical tradition kept descriptive terminology largely separate from narrative interpretation in technical contexts. Mythological associations existed in parallel cultural literature, but official astronomical records maintained a functional vocabulary. The celestial river was something to be measured, located, and referenced, not explained through story. This separation allowed the term to retain descriptive clarity. The choice of river over cloud is particularly instructive. Clouds are transient, amorphous, and localized. They change shape rapidly and do not impose consistent boundaries. The Milky Way exhibits none of these properties at the scale of human observation. Its shape is stable over centuries. Its path is consistent. Its width varies gradually, not chaotically. Rivers, by contrast, are persistent structures with recognizable courses. They may meander, widen, or narrow, but they remain coherent over long timescales. This makes the river analogy far more accurate for an extended galactic disk viewed edge-on. In modern astrophysics, the Milky Way's kinematics reveal large-scale ordered rotation, with stars orbiting the galactic center in a flattened disk. While this motion is not directly visible to the naked eye, its projection creates the continuous band that ancient observers described. The river metaphor unintentionally anticipates this dynamical reality by emphasizing flow and coherence rather than static accumulation. The survival of the celestial river concept across centuries of Chinese astronomical practice reflects its empirical adequacy. It allowed astronomers to communicate positional information efficiently and to integrate the Milky Way into a broader system of sky division. When later contact with Western astronomy introduced new theoretical explanations, the descriptive term remained compatible with updated understanding. The object still appears as a river-like band when viewed from Earth. In this way, Chinese astronomy provides a clear example of how careful observation can lead to terminology that remains valid even as explanatory frameworks evolve. The Milky Way as a river is not a poetic indulgence, but a concise description of a persistent, extended, structured feature whose visual behaviour matches that of a flowing divider across the sky. Indigenous Australian sky knowledge represents one of the longest continuous observational traditions of the night sky on Earth. It developed without writing, without instruments, and without formal mathematical notation, yet it encodes detailed, spatially accurate information about celestial structure accumulated over tens of thousands of years. Within this knowledge system, the Milky Way was not treated as a diffuse background or an abstract decoration of the sky. It functioned as a structured domain mapped with precision, continuity, and practical intent. The object modern astronomy identifies as the Milky Way was integrated into navigation, law, seasonal timing, and oral transmission systems in a way that reflects sustained empirical engagement rather than symbolic abstraction. Central to this system are songlines. Songlines are not stories in the narrative sense. They are mnemonic sequences encoding spatial information, ecological knowledge, and cultural lore. Each songline corresponds to a path across the landscape, linking water sources, landmarks, and resources. Crucially, many songlines have direct counterparts in the sky. The Milky Way serves as a primary scaffold for these celestial mappings because it is the most stable, extended, and geographically informative structure visible at night. From an observational standpoint, the Milky Way provides an ideal reference frame. It spans the entire sky, maintains a fixed orientation relative to the stars, and changes predictably with season and time of night. For societies without permanent built markers or written maps, such a feature offers a reliable coordinate system. By aligning terrestrial routes with celestial ones, knowledge could be transmitted orally across generations with minimal distortion. In many Indigenous Australian traditions, the Milky Way is not treated as a bright object, but as a domain structured by both light and darkness. This distinction is critical. Rather than focusing exclusively on the luminous portions of the band, observers paid close attention to the dark dust lanes embedded within it. These lanes are not gaps in stars, but regions where interstellar dust absorbs background starlight, producing coherent dark shapes against the brighter stellar field. Under dark skies, these features are prominent and stable, forming recognizable silhouettes. One of the most significant outcomes of this focus is the interpretation of dark sky figures. The most widely documented example is the emu in the sky, a large contiguous shape traced not by stars but by darkness. Its head is formed by the Coalsack Nebula near the Southern Cross, and its body extends along the dark rifts of the Milky Way toward the galactic center. This figure is not an imaginative overlay imposed arbitrarily. It follows the actual morphology of dust extinction regions with remarkable fidelity. From a modern astrophysical perspective, this represents one of the earliest recognitions of galactic structure through the absence of light rather than its presence. Identifying dark nebulae as meaningful components of the sky requires careful, repeated observation. These features do not shimmer or draw attention like bright stars. They emerge only when contrast sensitivity is high and light pollution absent. Recognizing them as stable structures implies long-term familiarity with the night sky under consistent conditions. This approach differs fundamentally from constellation systems that rely on connecting bright stars. Dark sky figures emphasize the distribution of interstellar matter rather than stellar points. In effect, they encode information about the Milky Way's internal structure, highlighting regions of high dust density that trace spiral arms and star-forming complexes. While Indigenous Australian observers did not conceptualize dust clouds or galactic arms, their perceptual classification aligns with real physical features. Songlines mapped onto these dark sky structures served practical functions. The orientation and seasonal visibility of specific Milky Way features correspond to ecological cycles on Earth. For example, the rising or setting position of certain dark shapes aligns with the timing of animal breeding, plant flowering, or resource availability. The emu in the sky's orientation relative to the horizon changes throughout the year, providing a visual calendar that links celestial motion to terrestrial events. This empirical linkage between sky and land does not require symbolic interpretation to be effective. It is a functional mapping. When a particular sky configuration appears, a corresponding action becomes appropriate. Over generations, these associations are tested and refined through lived experience. Incorrect correlations would fail to produce reliable outcomes and would be abandoned. The persistence of these mappings indicates their empirical success. The absence of written language did not limit the precision of this knowledge. Oral transmission, when structured through song, rhythm, and repetition, can preserve complex information with high fidelity. The sky itself acts as an external memory aid, As long as the Milky Way appears in the same form, the encoded information remains anchored to a stable visual reference. This reduces drift and distortion over time. The longevity of Indigenous Australian astronomical knowledge also reflects the stability of the night sky over human timescales. The large-scale structure of the Milky Way has not changed perceptibly in tens of thousands of years. Precession slowly alters the timing of when specific features appear, but their shapes and relative positions remain constant. This stability allows observational traditions to persist across immense spans of time without losing relevance. Importantly, this knowledge system does not rely on myth to function, even though mythological narratives often accompany it. The narratives serve as memory frameworks, not explanations of physical causation. The practical content lies in the alignment between sky features and environmental cues. In this sense, Indigenous Australian astronomy operates as an applied observational science embedded within cultural transmission. The emphasis on darkness as informative is particularly striking when viewed through a modern scientific lens. For much of the history of Western astronomy, dark regions of the sky were treated as empty or unimportant. Only in the 20th century did astrophysics fully recognize the role of dust in shaping galactic appearance and evolution. Indigenous Australian observers, by contrast, treated these regions as primary features. This inversion of emphasis reveals an alternative observational strategy tuned to low-light environments and holistic pattern recognition. Human vision, under scotopic conditions, is well suited to detecting extended dark shapes against faint luminous backgrounds. Rod cells are sensitive to contrast and motion, but not colour. In pristine dark skies, the Milky Way's dust lanes stand out clearly. The cognitive system naturally groups these dark regions into coherent forms. What distinguishes Indigenous Australian sky knowledge is the decision to treat those forms as meaningful and stable rather than incidental. Navigation provides another domain where the Milky Way's structure was exploited. On long journeys across open terrain, the orientation of the galactic band relative to the horizon offers directional information. Unlike individual stars, which move significantly over the course of a night, the Milky Way's axis remains fixed. This makes it a reliable guide for maintaining direction over hours of travel. Song lines that mirror this celestial axis encode both route and orientation. The empirical nature of this knowledge challenges assumptions about the relationship between writing and science. Writing allows for explicit calculation and accumulation of data, but it is not the only means of preserving accurate observational knowledge. In environments where the sky is consistently visible and culturally central, oral systems can achieve comparable functional precision through repetition and embodied practice. Indigenous Australian sky knowledge also demonstrates a form of distributed cognition. The environment, the sky, the landscape, and the human body all participate in the storage and transmission of information. The Milky Way is not merely observed, it is used as part of a cognitive infrastructure that links perception, memory, and action. This perspective reframes the Milky Way's role in human history. Rather than being merely named or mythologized, it functioned as a navigational framework, a calendar, and a map. The recognition of its internal structure through dark sky figures represents a level of observational engagement that parallels and in some respects anticipates modern astrophysical insights. The absence of written records means that this knowledge must be reconstructed through ethnography, oral histories, and comparative analysis. However, where such reconstructions are possible, they consistently reveal a sophisticated understanding of the sky grounded in repeated observation. The consistency of dark sky figures across distant regions suggests that these interpretations are responses to shared visual stimuli rather than localized inventions. From a scientific standpoint, Indigenous Australian interpretations of the Milky Way underscore the importance of considering multiple observational strategies. Focusing exclusively on bright points yields one kind of knowledge. Attending to extended structures and absences yields another. Both are valid, and both correspond to real physical properties of the galaxy. In summary, Indigenous Australian sky knowledge represents an empirical engagement with the Milky Way that emphasises structure, continuity, and functional relevance. Songlines mapped onto the galactic band encode spatial and temporal information with high reliability. The interpretation of dust lanes as dark sky figures reflects an early and accurate recognition of galactic structure through extinction. This knowledge developed without writing, sustained by stable environmental conditions and rigorous oral transmission. It stands as a powerful example of how long-term observation can yield scientifically meaningful understanding independent of formal theoretical frameworks. Mesoamerican civilizations encountered the Milky Way under observational conditions that differed fundamentally from those of higher latitudes, and those conditions shaped how the structure was interpreted and used. Situated near the tropics, observers in Mesoamerica regularly saw the Milky Way rise nearly vertically from the horizon and pass close to the zenith. This geometry transformed the band from a horizontal divider into an upright structure, encouraging its treatment as a cosmic axis rather than a boundary or road. The result was a conception of the Milky Way as a vertical organizer of space and time, integrated directly into calendrical systems, architecture, and ritual practice. The object modern astronomy identifies as the Milky Way appears as a great circle on the celestial sphere. Near the equator, great circles intersect the horizon at steep angles. When the brightest regions of the Milky Way, including the direction toward the galactic centre, were visible at night, the band often stood upright, extending from one horizon through the overhead sky to the opposite horizon. This configuration is not occasional but seasonal and predictable. It repeats year after year with high regularity, making it a reliable large-scale reference. In Mesoamerican cosmology, verticality carried structural meaning. The universe was organized into layered realms connected by an axis linking the underworld, the terrestrial plane, and the sky. A luminous vertical feature spanning the heavens naturally mapped onto this conceptual framework. The Milky Way's orientation provided a visible manifestation of an otherwise abstract organizing principle. Importantly, this interpretation is grounded in geometry before symbolism. The sky actually presents a vertical structure under these latitudes, and cultural meaning followed that observation. The timing of this vertical orientation is tied to Earth's orbital motion. As the year progresses, the nighttime sky faces different directions in space. The Milky Way's most vertical presentations coincide with specific seasons, often clustering around solstitial periods. In Mesoamerica, these periods were already of high importance due to their role in regulating agricultural cycles. The coincidence of solar extremes and prominent galactic configurations reinforced the Milky Way's role as a temporal marker. This alignment did not require precise angular measurement to be useful. Even coarse observation reveals when the band stands upright at dusk or midnight. Such moments are visually striking and easy to remember. When repeated annually, they form anchors in the ritual calendar. The Milky Way becomes a seasonal signal layered on top of solar and lunar cycles, adding redundancy and resilience to timekeeping systems. Architectural orientations in several Mesoamerican sites reflect this integration of sky geometry and ritual timing. Major structures were aligned not only to sunrise or sunset on key dates, but also to the orientation of the night sky. When viewed from specific ceremonial locations, the Milky Way's vertical axis would align with architectural axes, reinforcing the impression that built space mirrored cosmic structure. This alignment does not imply an abstract fascination with the galaxy as an object, but a practical desire to synchronize human activity with predictable celestial patterns. The Milky Way's intersection with the ecliptic also plays a role. Near the galactic centre, the band crosses the path of the Sun, Moon, and planets. These crossings are zones of visual density where multiple celestial motions overlap. In equatorial regions, these intersections often occur high in the sky, making them particularly prominent. the convergence of solar, lunar, planetary, and galactic paths at specific times enhances the perception of a central axis governing celestial motion. Ritual timing benefited from this convergence. Events scheduled near periods when the Milky Way stood vertically overhead would also coincide with specific solar positions. This coupling strengthened the association between sky configuration and terrestrial action. Agricultural planting, harvest rituals, and political ceremonies could be timed using multiple independent celestial cues, increasing reliability in the absence of written numerical calendars. The Milky Way's verticality also affects how motion is perceived. When the band stands upright, Earth's rotation causes stars to appear to move upward and downward along it rather than sideways across it. This visual effect enhances the sense of ascent and descent, aligning with cosmological models that emphasize vertical movement between realms. The perception arises from geometry and rotation, not narrative invention. Mesoamerican astronomical practice emphasized repeated observation from fixed sites. Temples and ceremonial platforms served as stable viewing points, allowing precise recognition of when specific alignments occurred. Over generations, this practice refined knowledge of the sky's seasonal behavior. The Milky Way's role as a large-scale structural feature made it particularly suitable for this kind of long-term tracking. Unlike individual stars, whose risings and settings are subtle and require careful attention, the galactic band is immediately apparent. The use of the Milky Way as a world axis also reflects its visual continuity. It does not fragment into isolated points, but maintains a connected form across the sky. This continuity supports the idea of a single axis linking multiple domains. In contrast, constellations composed of discrete stars are less effective for representing uninterrupted connection. The Milky Way's uninterrupted arc provides a natural visual metaphor for linkage, but again the metaphor follows the observation. Seasonal cycles in Mesoamerica are strongly tied to rainfall patterns rather than temperature extremes. The timing of rains is critical for agriculture, and celestial indicators that correlate with seasonal transitions are valuable. The changing nighttime orientation of the Milky Way provides such an indicator. Its vertical or inclined posture at dusk or midnight marks transitions that align with shifts in environmental conditions. Over time, these correlations would have been tested and retained only if they proved reliable. It is important to note that these uses of the Milky Way do not depend on treating it as a luminous substance. Its function is geometric and positional. Whether perceived as bright or faint, it serves as a reference line. This distinguishes Mesoamerican interpretations from those that emphasize texture or material analogy. The same physical object supports different conceptual roles depending on observational context. The influence of galactic orientation on architecture suggests an understanding of the sky as a stable, structured system rather than a backdrop for myth. Alignments require planning, measurement, and verification. Structures built to frame celestial events reflect confidence that those events will recur. The Milky Way's stability over human timescales makes it suitable for such planning. The vertical axis interpretation also integrates naturally with broader Mesoamerican spatial organization, where cardinal directions and vertical layers are central. The Milky Way provides a celestial counterpart to these organizing principles. Its path across the sky intersects cardinal directions at predictable points, reinforcing the grid-like structuring of space. From a modern astronomical perspective, the Milky Way's role as a world axis in equatorial cultures highlights how observer latitude shapes cosmological interpretation. The same galactic disk produces different dominant geometries when projected onto the sky from different locations on Earth. Near the equator, verticality dominates. At higher latitudes, horizontality and curvature are more prominent. Cultural interpretations track these perceptual differences closely. The Mesoamerican case demonstrates that large-scale galactic structure can influence not only naming but built environments and ritual systems. The Milky Way's predictable orientation provided a scaffold for synchronizing human activity with celestial cycles. This scaffold did not require an understanding of galaxies as physical systems. It required only sustained observation, stable skies, and the recognition that certain patterns repeat. In this context, the Milky Way functions as an organizing axis rather than an object of curiosity. Its importance lies in what it enables: alignment, timing, and coherence between sky and land. The vertical cosmic structure observed by Mesoamerican civilizations emerges directly from the interaction between Earth's latitude, the galaxy's disk geometry, and human pattern recognition. In northern Europe, the Milky Way was encountered under observational conditions that emphasized length, continuity, and traversal rather than division or verticality. At high latitudes, the geometry of the sky reshapes how extended celestial structures are perceived. The galactic band rarely passes overhead. Instead, it stretches low across the sky, often arcing close to the horizon and remaining visible for long periods of the night. This geometry transforms the Milky Way into an elongated feature that reads naturally as a road, path, or bridge, rather than a boundary or axis. The object modern astronomy identifies as the Milky Way presents itself as a great circle projected onto the celestial sphere. Near the poles, great circles intersect the horizon shallowly. The result is a flattened arc that appears to wrap around the observer rather than rise above them. In northern Europe, this produced a visual experience dominated by horizontal extension. The band appears long, continuous, and traversable, emphasizing direction over separation. This appearance is reinforced by seasonal effects unique to high latitudes. During summer months, astronomical twilight can persist through much of the night, reducing contrast and muting the Milky Way's brightness. When it is visible, it appears as a faint, stretched ribbon rather than a bold, textured structure. In winter, when darkness is prolonged, the band becomes clearer but remains low and elongated. The repeated experience of a long, low arc across the sky encourages interpretation in terms of pathways rather than vertical structures. Norse and other Northern European traditions reflect this geometry directly. The Milky Way is frequently described as a road or bridge, a feature that connects regions rather than divides them. This is not an abstract metaphor imposed on the sky. It mirrors the perceptual reality of a luminous band that seems to span from one edge of the world to another. The sky, under these conditions, reads as a landscape, and the Milky Way reads as infrastructure within it. Environmental context strengthens this interpretation. In northern regions, travel routes were defined by narrow passages through forests, along coastlines, or across frozen terrain. Roads and bridges were critical features of survival and communication. A long, continuous structure guiding movement resonates with lived experience. When such a structure appears in the sky with comparable scale and persistence, the analogy becomes intuitive. The bridge interpretation is further encouraged by the Milky Way's interaction with other celestial features. Bright stars and constellations appear to lie along or near the band, as if stationed beside a route. The moon and planets cross it repeatedly, reinforcing the impression of traffic along a fixed path. These crossings are especially noticeable when the band is low, because the motion appears lateral rather than vertical, mimicking terrestrial travel. High-latitude visibility also accentuates the Milky Way's apparent thickness variation along its length. Near the direction of the galactic center, which remains relatively low in northern skies, the band thickens and brightens slightly. Elsewhere it thins and fades. This gradient reads naturally as a road that widens and narrows rather than as a uniform strip. The eye follows it horizontally, tracing its course across the sky. The absence of a strong overhead presentation is crucial. Without a moment when the Milky Way stands upright or dominates the zenith, it does not naturally suggest an axis connecting layers of the universe. Instead, It remains peripheral yet extensive, always present but rarely intrusive. This supports interpretations centered on passage and connection rather than hierarchy or division. Norse cosmology emphasized connectivity between realms through defined routes. This emphasis aligns closely with the sky's presentation. A bridge-like Milky Way provides a visual anchor for the idea that movement between domains follows a specific path. The metaphor does not arise from speculative storytelling, but from a stable visual cue repeatedly encountered under consistent environmental conditions. The persistence of this interpretation across Northern Europe suggests a shared perceptual foundation. While specific names and narratives varied, the underlying concept of the Milky Way as a road or bridge appears in multiple traditions. This convergence is best explained by shared latitude and shared sky geometry, rather than cultural transmission alone. Climate also plays a role. Long winters with extended darkness increase exposure to the night sky. During these periods, outdoor activity, travel, and observation occur under starlight. The Milky Way becomes a frequent companion rather than an occasional sight. Its role as a navigational or orienting feature is reinforced by necessity. A long, continuous band provides directional context even when individual stars are obscured by clouds or low contrast. Atmospheric effects at high latitudes further shape perception. Low elevation viewing increases atmospheric extinction, softening brightness and smoothing texture. Dust lanes become less prominent than in equatorial or southern skies. The band appears more uniform and less internally structured. This visual simplification favours interpretations based on continuity rather than internal detail. Roads and bridges are defined by their extent, not by fine texture. The metaphor selection is therefore constrained by observation. A sky dominated by a low, stretched, relatively uniform band invites linear interpretations. A sky where the band stands vertical or divides hemispheres invites different ones. The Norse and Northern European case illustrates how environmental factors filter astrophysical reality into culturally resonant forms without distorting the underlying structure. From a modern perspective, this interpretation aligns well with the Milky Way's physical nature as a rotating disk. While the rotation is not directly visible, the disk's projection produces the elongated arc that ancient observers described. The idea of a path or road captures the disk's coherence and continuity more accurately than metaphors implying amorphous spread. The endurance of the road or bridge interpretation reflects its functional adequacy. It allows the Milky Way to be referenced, remembered, and integrated into broader cosmological frameworks without contradiction from observation. As long as the sky continues to present the band in this elongated form at high latitudes, the metaphor remains stable. In summary, Norse and Northern European interpretations of the Milky Way arise directly from high-latitude viewing geometry, prolonged darkness, and environmental familiarity with linear infrastructure. The Milky Way appears as a long, low arc, encouraging its treatment as a road or bridge across the sky. This interpretation is not a poetic imposition, but a perceptual response shaped by latitude, atmosphere, and lived experience. Astronomy during the Islamic Golden Age represents one of the most important periods of continuity and refinement in the history of observational science. Rather than replacing earlier Greek astronomical concepts, scholars working across the Islamic world preserved, corrected, expanded, and systematized them with a level of precision unmatched in earlier eras. Within this tradition, the Milky Way remained a recognized, named, and carefully situated feature of the sky. Its descriptive identity persisted, even as instruments improved and observational accuracy increased, not because of conservatism, but because the original descriptor continued to match the empirical appearance of the phenomenon. Islamic astronomy inherited Greek astronomical texts through large-scale translation efforts centered in institutions such as the House of Wisdom in Baghdad. Works by Aristotle, Hipparchus and Ptolemy were translated into Arabic, scrutinized, and subjected to critical analysis. These texts included descriptions of the fixed stars, the structure of the celestial sphere, and extended features such as the Milky Way. Importantly, the translations aimed to preserve technical meaning rather than literary style. Terminology was chosen carefully to ensure that observational descriptors remained accurate and unambiguous. The object modern astronomy identifies as the Milky Way entered Islamic astronomical literature as an established feature of the celestial sphere. It was treated neither as a mythological remnant nor as a vague background glow. Instead, it occupied a defined place within a geometric and mathematical framework. Scholars were concerned with its position relative to the ecliptic, the zodiac, and known star groupings. The Milky Way was mapped, referenced, and discussed as part of the sky's fixed structure. One of the defining characteristics of Islamic Golden Age astronomy was the emphasis on precise positional measurement. Astronomers developed improved astrolabes, armillary spheres, quadrants, and observational techniques that allowed for more accurate determination of stellar coordinates. Observatories in cities such as Baghdad, Damascus, Samarkand, and later Maraga enabled sustained, systematic observation. These advances refined knowledge of star positions, precession, and planetary motion. However, they did not fundamentally alter the naked eye appearance of the Milky Way. This is a crucial point. Improved instruments increased angular precision, but did not increase resolving power in a way that would transform the Milky Way's appearance. Telescopic resolution remained unavailable. As a result, the Milky Way continued to appear as a diffuse, pale band composed of unresolved light. The empirical stimulus remained the same, and so the descriptive term inherited from Greek astronomy remained valid. Islamic astronomers were keenly aware of the distinction between descriptive appearance and underlying cause. Many texts discuss the Milky Way in terms of its visual properties without asserting a definitive physical explanation. Some scholars debated whether it was composed of vapours, densely packed stars, or some other luminous medium. These debates did not undermine the name. The term milky described what was seen, not what was theorized. The persistence of the milky descriptor reflects a broader methodological principle in Islamic science. Observational description precedes causal explanation. Names anchored in stable appearances were retained even as theoretical interpretations evolved. This approach avoided unnecessary renaming that could obscure continuity between observations across generations and regions. Detailed sky mapping during this period reinforced the Milky Way's identity as a coherent structure. Star catalogues expanded upon earlier Greek lists, increasing the number of recorded stars and improving positional accuracy. The Milky Way's path across the sky was traced relative to these stars, noting where it thickened, thinned, or split. These features were not dismissed as imperfections, but treated as intrinsic aspects of the structure. The presence of dark rifts and variations in brightness was recognized, even if their physical origin was unknown. Terminology transmission played a key role in maintaining consistency. Arabic astronomical language often translated Greek terms conceptually rather than phonetically, preserving descriptive meaning. Where Greek used a term derived from milk, Arabic equivalents conveyed the same visual quality. This ensured that scholars working in different languages could refer to the same phenomenon without ambiguity. The Milky Way's name thus functioned as a stable label across a multilingual scientific community. Islamic astronomers also placed strong emphasis on correcting errors in inherited texts. Ptolemy's star catalogue, for example, was known to contain inaccuracies due to precession and observational limitations. Scholars recalculated positions and adjusted models accordingly. Yet even as coordinates were corrected, the Milky Way's descriptive treatment remained unchanged. Its large-scale structure was not subject to the same kinds of numerical correction because it was not defined by precise boundaries or point positions. It was defined by continuous appearance. The development of spherical trigonometry and improved celestial coordinate systems further clarified the Milky Way's role in the sky. Astronomers could describe its inclination relative to the celestial equator and its intersection with the ecliptic. These descriptions reinforced its identity as a great circle-like feature on the celestial sphere. The Milky analogy continued to function as an efficient shorthand for this extended diffuse band. Islamic scholars also recognized the Milky Way's interaction with other celestial phenomena. Lunar and planetary crossings were noted, as were the paths of comets. These observations underscored the Milky Way's status as a background structure against which motion could be detected. Its stability made it a reference frame rather than an object of motion. This role further justified retaining a descriptive name tied to appearance rather than behavior. The persistence of the Milky concept, despite improved instruments, highlights an important limitation of pre-telescopic astronomy. Without resolving power sufficient to separate the band into individual stars, no observational evidence compelled a change in terminology. The name remained empirically accurate at the scale accessible to observers. This contrasts with later periods, when telescopes revealed new structures that required new language. Islamic Golden Age astronomy also served as a transmission bridge to later European science. Texts translated into Latin during the medieval period carried forward not only numerical data and models, but also terminology. The Milky Way's name, already stabilized through centuries of use, passed unchanged into European scholarly tradition. By the time telescopic astronomy emerged, the term was deeply embedded in scientific language. From a modern perspective, this continuity appears remarkably robust. The Milky Way's name survived multiple cultural transitions, linguistic shifts, and theoretical revolutions. Islamic astronomers played a critical role in this survival by treating astronomical language as a tool for precision rather than ornamentation. They preserved names that worked and refined the frameworks around them. In summary, Islamic Golden Age astronomy maintained the Milky descriptor for the Milky Way because it remained observationally valid, linguistically efficient, and conceptually neutral. Improved instruments enhanced positional accuracy, but did not alter the galaxy's naked eye appearance. Detailed sky mapping reinforced its identity as a coherent, diffuse band. Terminology transmission ensured consistency across languages and regions. The result was a seamless continuity in naming that bridged ancient Greek observation and modern astrophysical understanding without contradiction. In medieval Europe, the name of the Milky Way effectively stopped evolving because the observational, linguistic, and institutional conditions required for renaming were absent. This was not the result of ignorance or stagnation, but of a stable equilibrium between what could be seen, how knowledge was transmitted, and what counted as legitimate authority in astronomy. The celestial feature already known as the Milky Way occupied a category of phenomena that were considered complete, settled, and not in need of reinterpretation. Its appearance had not changed, the tools for probing it further did not yet exist, and the intellectual frameworks governing astronomy discouraged speculative revision without new evidence. Medieval European astronomy inherited its core content almost entirely through classical and Islamic sources. Greek and Latin texts, often mediated by Arabic scholarship, formed the backbone of astronomical education. These texts arrived with established terminology that was treated as canonical. The Milky Way, named and described consistently for centuries, entered medieval curricula as a known object with a known name. In an intellectual culture that valued preservation and commentary over innovation, changing such a name would have required a compelling reason grounded in observation. No such reason was available. The astronomical environment of medieval Europe reinforced this stability. Observations were still conducted with the unaided eye or simple sighting instruments. These tools were sufficient for tracking planetary motion, eclipses, and stellar risings, but they offered no new insight into the nature of diffuse celestial structures. The Milky Way continued to appear as a pale, continuous band. Without increased resolving power, its visual character remained identical to that described by earlier observers. The descriptive accuracy of the existing name remained intact. Astronomical conservatism during this period was methodological rather than ideological. Medieval scholars operated within a framework that distinguished between phenomena subject to change and those considered part of the fixed order of the heavens. Planets moved, comets appeared and disappeared. The Milky Way did neither. It was always present, always in the same place relative to the fixed stars. This constancy placed it in the category of immutable celestial features. Objects in this category were described, not questioned. Educational institutions further entrenched this conservatism. Astronomy was taught as part of the quadrivium, alongside arithmetic, geometry, and music. Its purpose was not discovery, but understanding the mathematical harmony of the cosmos. Texts were studied line by line with emphasis on faithful interpretation rather than revision. Terminology functioned as a stable reference system. Altering names would have disrupted the coherence of this system without offering pedagogical benefit. The transmission of astronomical knowledge relied heavily on manuscript copying. Each copying process favoured fidelity over creativity. Scribes reproduced established terms exactly, reinforcing linguistic stability across generations. Marginal commentaries expanded on meaning but rarely replaced core vocabulary. The Milky Way's name, embedded in authoritative texts, propagated unchanged through this process. Even regional vernacular expressions tended to mirror the Latin formulation rather than invent new descriptors. The absence of systematic observational programs also contributed to the freezing of the name. While medieval astronomers made careful observations for calendrical and astrological purposes, there was little incentive to re-examine features that showed no apparent variation. Resources were directed toward refining tables, predicting conjunctions, and reconciling models with doctrine. The Milky Way, offering no new data points and posing no immediate theoretical challenge, remained untouched. Theological considerations played an indirect role. Medieval cosmology integrated astronomy into a broader metaphysical system in which the heavens reflected divine order. Stability was a feature, not a flaw. A celestial structure that appeared constant over centuries reinforced this worldview. Renaming it or reinterpreting it without new evidence would have introduced unnecessary uncertainty. The existing name, inherited from respected authorities, was sufficient. It is important to note that this conservatism did not imply a lack of observational awareness. Medieval observers were keenly attentive to the sky. They tracked the Milky Way's seasonal visibility, noted its orientation, and used it as a reference in describing other phenomena. Its role as a backdrop for planetary motion and cometary paths was well understood. What did not change was the conceptual framing of the band as a diffuse, milky structure rather than a collection of discrete objects. The freezing of the name also reflects a linguistic threshold. By this period, the term had permeated multiple languages and cultural contexts. Latin Via Lactea had equivalents in vernacular speech, each preserving the milky descriptor. Once a term reaches this level of diffusion, renaming becomes impractical unless driven by a dramatic shift in understanding. The medieval period lacked such a shift with respect to the Milky Way. Astronomical instruments of the time reinforced this inertia. Devices like the astrolabe and armillary sphere were designed to model the celestial sphere, not to resolve extended objects. They excelled at representing circles, angles, and motions. The Milky Way, being an extended luminous region without sharp boundaries, did not lend itself to further analysis with these tools. It remained a qualitative feature rather than a quantitative one. The Milky Way's status as a fixed celestial constant also shaped how it was discussed in scholarly writing. References to it are often brief and descriptive, assuming familiarity. Authors did not feel compelled to explain or redefine it. This tacit understanding indicates that the object's identity was considered settled. Its name functioned as a pointer to a shared visual experience rather than a hypothesis. When unusual celestial events occurred, such as bright comets or temporary stars, they were explicitly contrasted with the fixed stars and the Milky Way. This contrast reinforced the latter's role as part of the unchanging celestial framework. By serving as a baseline against which change was measured, the Milky Way's conceptual position became even more rigid. The freezing of the name persisted until the introduction of telescopic observation. Only when instruments capable of resolving the band into countless faint stars became available did the possibility of reinterpretation arise. Until that moment, the Milky Way remained observationally opaque. Its surface brightness distribution could be described but not decomposed. The existing name continued to map accurately onto the perceptual reality accessible to observers. This period of stability had long-term consequences. Because the name was preserved without modification, later astronomers inherited a terminology that bridged pre- and post-telescopic eras. The transition to a new understanding of the Milky Way did not require linguistic disruption. The name already described the phenomenon at the scale of human perception, even if its physical explanation changed. The medieval freezing of the Milky Way's name therefore represents a natural outcome of stable observation, conservative knowledge transmission, and the absence of disruptive instrumentation. The celestial band remained what it had always been to the eye, a pale, continuous feature spanning the sky. In such conditions, naming reached an equilibrium, and that equilibrium held until new tools altered what could be seen. The introduction of the telescope at the beginning of the 17th century produced the first genuine rupture between the inherited visual description of the Milky Way and its underlying physical explanation. For the first time, an instrument altered what could be seen rather than merely refining positional accuracy. This moment is often described as a revolution, but in the case of the Milky Way, the revolution was asymmetric. The explanation changed fundamentally, while the name did not. Understanding why requires close attention to what telescopes actually revealed, what they did not, and how scientific language behaves when observation advances faster than perception. When Galileo Galilei turned his telescope toward the Milky Way in 1609 to 1610, he did not observe a new object. He observed the same luminous band that had been visible for millennia, but he observed it at a different scale. Through magnification, the diffuse glow resolved into a mass of innumerable stars, tightly packed and individually faint. This was not a reinterpretation of brightness or texture. It was a decomposition. What had appeared as a continuous pale substance was revealed to be the combined light of countless discrete sources. This discovery directly invalidated earlier physical explanations that treated the Milky Way as a luminous fluid, vapor, or reflection. However, it did not invalidate the perceptual description on which the name was based. To the naked eye, the Milky Way still appeared milky. Even through early telescopes, much of the band remained unresolved. The instrument could pierce the glow only partially. Large regions still appeared as haze beyond the resolving power of the optics. The visual experience that had generated the name remained intact for everyday observation. The telescope therefore introduced a layered understanding. At low resolution, the Milky Way is a diffuse band. At higher resolution, it is a dense stellar field. These two descriptions are not mutually exclusive. They operate at different observational scales. The name refers to the former, while the explanation addresses the latter. This separation allowed the term to survive without contradiction. Galileo's observations also revealed an important asymmetry between point sources and extended sources. Telescopes dramatically enhance the visibility of stars by concentrating light and increasing angular resolution. Extended low-surface brightness features, however, do not benefit in the same way. Magnification spreads their light over a larger area of the retina or detector, often reducing contrast. As a result, even improved instruments did not transform the Milky Way's appearance as completely as they transformed the appearance of planets or the Moon. This limitation meant that the Milky Way remained visually milky even in the age of early telescopes. Astronomers could demonstrate that it was composed of stars, but they could not make it stop looking like a luminous band. The perceptual stimulus that anchored the name persisted. The survival of the name also reflects the function of terminology in science. Names are primarily tools for reference, not explanations. They allow researchers to point to the same object across time, language, and theoretical frameworks. Once a name becomes widely adopted and unambiguous, changing it introduces friction. In the case of the Milky Way, there was no ambiguity about what the term referred to. The object was the same before and after telescopic resolution. Only its interpretation changed. Scientific language therefore exhibits inertia. This inertia is not conservatism for its own sake, but a stabilizing mechanism. Renaming is reserved for cases where an object is shown to be fundamentally misidentified, split into multiple entities, or conflated erroneously. The Milky Way did not meet these criteria. It was not discovered to be something else. It was discovered to be more of what it already appeared to be. The telescope also did not immediately reveal the full structure of the galaxy. Early observers could not see spiral arms, a central bar, or a halo. They could not measure distances to stars within the Milky Way reliably. Without these additional layers of structure, there was no new macroscopic form that demanded a new name. The band across the sky remained the dominant large-scale feature. As telescopes improved through the 17th and 18th centuries, astronomers extended Galileo's insight without replacing the inherited vocabulary. They mapped star densities along the band, noted variations in brightness, and identified regions of exceptional concentration. Yet these refinements operated within the existing descriptive framework. The Milky Way was now understood as a stellar system, but it was still the same luminous feature. This pattern reflects a broader principle in the history of science. Explanatory revolutions do not automatically trigger linguistic revolutions. Terms anchored in stable sensory experience tend to persist even when their theoretical underpinnings change. The word sunrise survived heliocentrism. Heavy survived Newtonian mechanics. In each case, language tracks perception more closely than explanation. The Milky Way is a particularly strong example because the perceptual experience is shared by all observers on Earth. Regardless of theoretical training, anyone under a dark sky sees the same band. A name grounded in that experience has exceptional staying power. Changing it would require replacing a universally accessible descriptor with one tied to abstract theory, which would reduce communicative efficiency rather than improve it. Astronomers also had pragmatic reasons to preserve continuity. Scholarly literature accumulated rapidly after the invention of printing. Names that appeared in star atlases, observational logs, and educational texts became embedded in a growing corpus. Altering terminology would have fragmented that corpus, complicating cross-referencing and historical comparison. Retaining established names allowed new discoveries to be integrated seamlessly into existing frameworks. The Milky Way's name also avoided premature specificity. It did not encode an incorrect physical claim in the way some older terms did. It described appearance, not cause. This neutrality made it robust. Even as astrophysics advanced and the galaxy was recognized as one among many, the name remained accurate at the level it claimed to describe. The eventual recognition that the Milky Way is a galaxy comparable to external nebulae introduced another potential naming disruption. Yet even then, the name survived. Astronomers distinguished between the Milky Way as a galaxy and the Milky Band as its projection on the sky, using context rather than renaming to manage the distinction. The term expanded in meaning rather than being replaced. This expansion reflects another aspect of linguistic inertia. Successful terms accumulate meaning instead of being discarded. Milky Way came to refer both to the visual band and to the entire galactic system. This dual usage persists because it rarely causes confusion. The context of discussion usually makes clear whether one is referring to the appearance in the sky or the astrophysical structure as a whole. The telescope therefore did not break the metaphor by rendering it false. It broke it by revealing that the metaphor was incomplete. The milky appearance is not the substance itself, but the emergent result of unresolved structure. Once this was understood, the metaphor became descriptive rather than explanatory. Its role shifted, but its utility remained. In scientific practice, such shifts are common. Terms outlive the theories that first motivated them because they continue to serve as efficient handles on complex phenomena. The Milky Way's name exemplifies this process. It survived not because astronomers were reluctant to abandon tradition, but because the name continued to do its job. As instruments advanced further, revealing dust lanes, stellar populations, and galactic rotation, the distance between name and explanation grew larger. Yet the original observational condition never disappeared. The galaxy still presents itself to human vision as a Milky Band. As long as that remains true, the name remains grounded. The telescope transformed humanity's understanding of what the Milky Way is, but it did not transform how the Milky Way appears to unaided human perception. Scientific language, shaped by the need to bridge expert knowledge and shared experience, preserved the name that linked both. Modern astrophysics transformed the Milky Way from a descriptive feature of the night sky into a quantified physical system governed by dynamics, composition, and long-term evolution. Yet despite this transformation, the name remained unchanged. This persistence reflects a structural feature of scientific language. Names anchored in stable observational experience can coexist indefinitely with increasingly abstract physical understanding. The Milky Way, now recognized as a rotating spiral galaxy with complex internal structure, continues to be referred to by a term that originated in naked eye appearance because the name and the explanation operate at different levels of description. In contemporary astrophysics, the Milky Way is understood as a barred spiral system composed of multiple stellar components with distinct kinematic and chemical properties. The thin disk hosts most ongoing star formation and contains young, metal-rich stars orbiting the galactic center on nearly circular paths. The thick disk contains older stellar populations with larger vertical velocity dispersions. Surrounding these disks is a diffuse stellar halo populated by metal-poor stars on eccentric orbits, along with globular clusters and stellar streams that record the galaxy's accretion history. Enclosing all of this is a massive dark matter halo that dominates the gravitational potential and governs rotation at large radii. Radio astronomy, infrared surveys, and astrometric missions have made this structure measurable. Observations of neutral hydrogen using the 21 centimeter line revealed the spiral pattern of the disk by tracing gas clouds beyond the reach of optical surveys. Infrared observations penetrated dust extinction, allowing astronomers to map stellar density toward the galactic center. Precision astrometry measured proper motions and parallaxes for millions of stars, converting the Milky Way from a projected band into a three-dimensional dynamical system. Galactic rotation curves provided one of the clearest demonstrations that the Milky Way is not simply a luminous disk of stars. Measurements showed that orbital velocities remain approximately constant far beyond the visible edge of the disk, implying the presence of a dominant non-luminous mass component. This discovery redefined the Milky Way's physical nature without altering its observational identity. The galaxy remained the same object in the sky, only its inferred mass distribution changed. Spiral structure added another layer of complexity. The Milky Way's spiral arms are not rigid material features, but density waves through which stars and gas pass. Star formation is enhanced as gas is compressed in these regions, producing luminous young clusters that trace the arms' locations. From within the disk, these structures contribute to the patchy brightness of the Milky Way band, particularly in regions where spiral arms are tangent to the line of sight. The visible star clouds correspond directly to these tangencies, linking modern galactic dynamics to ancient naked-eye impressions. Stellar populations further explain the Milky Way's integrated appearance. The surface brightness of the galactic plane is dominated not by the most luminous stars, but by vast numbers of moderate luminosity stars whose combined emission produces a smooth glow. Dust selectively removes blue light and redistributes energy into infrared wavelengths, shaping the spectrum that reaches human eyes. These processes ensure that even with full physical understanding, the galaxy's visible manifestation remains diffuse and pale under dark skies. Given this depth of physical knowledge, the continued use of the name Milky Way might appear anachronistic. However, scientific nomenclature is not designed to encode full explanations. It is designed to provide stable reference. The name identifies an object across contexts, disciplines, and levels of expertise. In this role, Milky Way performs effectively. It unambiguously refers to the galaxy containing the solar system, regardless of whether the discussion concerns stellar dynamics, chemical evolution, or cosmology. The gap between nomenclature and physical understanding is therefore functional rather than problematic. Many scientific terms operate this way. Names are often assigned early based on appearance or limited information and persist as understanding deepens. Replacing them would not improve clarity, it would sever continuity. In the case of the Milky Way, no alternative name could match its communicative efficiency. A term describing spiral density waves, dark matter halos, and stellar kinematics would be unwieldy and unnecessary for identification. The name also retains relevance because it continues to describe a real observational phenomenon. From Earth, the galaxy still presents itself as a milky band across the sky when viewed under suitable conditions. This appearance is not an artifact of ignorance. It is a consequence of geometry, stellar distribution, and human vision. Modern astrophysics explains why the band looks the way it does, but it does not make the band disappear. The name remains anchored to a persistent sensory experience. Astrophysics has, however, clarified the distinction between the Milky Way as an object and the Milky Way as an appearance. In technical contexts, astronomers specify whether they are referring to the galactic disk, the stellar halo, or the projected band of integrated light. This precision is achieved through context and qualifiers rather than renaming. The base term remains intact, supporting communication across subfields. The acceptance of this gap also reflects maturity in scientific practice. Early science often sought to align names tightly with explanations, leading to frequent renaming as theories changed. Modern science recognizes that stability in terminology facilitates cumulative knowledge. As long as a name does not encode a demonstrably false claim, it can remain useful even if its original motivation becomes obsolete. In cosmology, the Milky Way now occupies a specific position as one galaxy among hundreds of billions. It is no longer the universe's central structure, nor even a particularly unusual galaxy. Yet its name remains distinct because it identifies our local environment. The term functions as a proper noun rather than a category label. It points to a specific system, not to a class of objects. This proper noun status further insulates it from pressure to change. The name's persistence also reflects the layered nature of astronomical knowledge. At one layer lies immediate human perception, At another lies instrumental observation. At another lies theoretical modelling. These layers do not replace one another, they coexist. The Milky Way's name belongs primarily to the perceptual layer, which remains relevant even as deeper layers expand. Modern surveys continue to reinforce this layering. All sky maps in different wavelengths reveal radically different aspects of the galaxy, yet optical images intended for public communication often resemble what ancient observers saw, a luminous band against darkness. This continuity reinforces the appropriateness of the inherited name. It remains the most efficient bridge between expert understanding and shared human experience. The retention of the name also avoids false precision. Any attempt to rename the Milky Way based on current physical models would embed assumptions that may later require revision. Dark matter distribution, spiral arm structure, and bar dynamics are active areas of research. A name tied to a particular model could become outdated. Milky Way, by contrast, is model agnostic. It commits only to appearance and identity. As astrophysics advances toward increasingly abstract descriptions involving simulations, phase space distributions, and cosmological context, the gap between name and explanation will widen further. Yet this widening does not diminish the name's usefulness. It underscores its role as an anchor rather than a summary. The Milky Way remains a point of reference through which complex ideas can be communicated without redefining the object itself. In practice, this stability allows the history of discovery to remain legible. Observations from different centuries can be compared without translation. A medieval reference to the Milky Way and a modern measurement of its rotation curve clearly refer to the same entity. This continuity is essential for historical coherence in science. Modern astrophysics therefore does not merely tolerate the inherited name, it benefits from it. The name encapsulates a perceptual truth that remains valid, while the science explains the mechanisms behind that truth. The two coexist without conflict because they answer different questions. One identifies what is seen, the other explains why it is seen. Across human history, cultures separated by oceans, millennia, and languages converged on strikingly similar ways of naming the same celestial structure. This convergence did not arise from shared myths or cultural diffusion alone. It arose because human perception, operating under similar biological constraints and exposed to the same physical stimulus, tends to organize visual information in predictable ways. The Milky Way provides a uniquely clean test case for this process because it is a large-scale, persistent, and globally visible feature whose appearance is dominated by geometry and physiology rather than by interpretation. The object now known as the Milky Way presents itself to the naked eye as an extended, continuous luminance structure with internal texture and variable thickness. It is neither a point nor a compact shape. It has no sharp boundaries and no obvious centre when seen from Earth. These properties constrain the range of plausible perceptual categories into which it can be placed. Human vision is optimized to detect edges, gradients, continuity, and contrast. When presented with a stimulus that is elongated, continuous, and internally structured, the visual system tends to classify it as a path, a band, a flow, or a divider. Independent cultures repeatedly arrived at metaphors involving roads, rivers, milk, bridges, smoke, ash, or sky-spanning substances. These are not arbitrary poetic choices. They are drawn from a limited set of material categories that share key visual properties with the stimulus: continuity, diffuse brightness, and extension across space. The convergence is statistical rather than coincidental. Given the same input and the same sensory apparatus, the range of stable outputs narrows. This convergence reveals more about human perception than about mythology. Mythological narratives differ widely across cultures, but the basic visual metaphors applied to the Milky Way show strong clustering. Where cultures diverge, the divergence tracks environmental and geometric factors such as latitude, atmospheric clarity, and seasonal visibility. Where they converge, they do so despite those differences, reflecting shared perceptual constraints. Human pattern recognition operates by grouping sensory input into coherent wholes. In low-light conditions, this process emphasizes global structure over fine detail. Rod-dominated vision suppresses color and sharpness while enhancing sensitivity to extended luminance gradients. The Milky Way falls squarely into this perceptual regime. It is processed not as a collection of discrete elements, but as a single structured entity. This processing bias makes it likely that observers will name the whole before understanding the parts. The brain's tendency to impose structure is not a flaw, it is a necessary adaptation. In environments where information is incomplete or noisy, extracting stable patterns is more valuable than resolving fine detail. The Milky Way is a stable pattern. It repeats nightly and seasonally with predictable changes. Its internal features remain fixed relative to one another. This stability allows the brain to treat it as an object rather than as random variation. Once an object is perceptually stabilized, language follows. Naming is an act of compression. It reduces a complex sensory input into a label that can be stored, communicated, and reused. The name need only capture the most salient features at the scale of perception. For the Milky Way, those features are extension, continuity, and diffuse brightness. Whether the name references milk, water, dust, or a path, it encodes these same properties. The repeated emergence of similar names across cultures therefore reflects convergent data compression. Different societies compress the same sensory input using similar perceptual primitives. The differences lie in which familiar material category was most salient in each environment, not in the underlying structure being described. This pattern undermines the idea that shared naming implies shared mythology. Mythology operates at a narrative level, embedding meaning, agency, and causation. The Milky Way's naming converges at a pre-narrative level. It occurs before agency is assigned, before stories are told, and before explanations are proposed. It is a response to appearance, not to meaning. The Milky Way also exposes a common misconception about early human thought, that explanation precedes observation. In practice, the opposite is true. Observation precedes explanation by necessity. One must first stabilize a perceptual object before asking what it is or why it exists. Across cultures, the Milky Way was first identified as a thing, then named, then incorporated into cosmologies, calendars, and narratives. The name marks the completion of the first step, not the last. Even when explanations differed dramatically, the perceptual object remained the same. Some cultures treated the Milky Way as a boundary, others as a route, others as a substance. These interpretations diverge at the level of function and meaning, but they converge at the level of form. The form constrains the interpretation space. This constraint becomes clearer when compared to other celestial phenomena. Constellations show far less convergence across cultures because they are constructed from discrete points whose grouping is underdetermined. Planets converge more strongly in naming and interpretation because they share distinctive behaviors. The Milky Way sits between these extremes. It is not a point source, but it is not arbitrary. Its large-scale structure forces recognition while allowing interpretive flexibility. The recognition of dark structures within the Milky Way provides an even more telling example. Only cultures with sustained exposure to pristine dark skies and long observational traditions consistently identified dust lanes as primary features. Where this occurred, interpretations converged on dark sky figures rather than bright star groupings. This convergence tracks sensory availability, not cultural preference. It shows that when the stimulus changes, so does the pattern of interpretation, but the mechanism remains the same. Modern cognitive science frames this process in terms of affordances. A visual stimulus affords certain interpretations more readily than others. The Milky Way affords interpretations involving continuity and traversal. It does not afford interpretations involving compactness or isolation. Human cognition exploits these affordances efficiently. The Milky Way therefore functions as a natural experiment in perception. It provides a fixed stimulus presented to the same species under varying but comparable conditions. The resulting naming patterns reveal which aspects of perception are robust and which are contingent. Robust features produce convergence, contingent features produce variation. This perspective reframes ancient sky knowledge as observational rather than speculative. Cultures were not inventing meanings to project onto the sky. They were responding to a stable perceptual input using the cognitive tools available to them. Mythology emerges later, layering causation and narrative onto an already named structure. The name itself records the moment when perception crystallized into recognition. The persistence of the name into modern science further reinforces this sequence. Even after physical explanations became available, the perceptual anchor remained useful. The name continued to refer to the same stabilized object. Science did not erase the perceptual layer, it built beneath it. The gap between what the Milky Way looks like and what it is physically is not a failure of early observers. It is a consequence of scale. Human perception operates at angular scales and brightness regimes far removed from galactic dynamics. Names derived from perception are therefore not wrong. They are scoped. They describe the phenomenon at the scale where it is experienced. This scaling principle applies broadly in science. Macroscopic descriptions remain valid even when microscopic explanations are discovered. The Milky Way is an extreme case because the microscopic explanation involves billions of components and processes invisible to unaided senses. The perceptual description survives because it still describes what is actually seen. Across cultures, the sequence repeats: observe, stabilize, name, then explain. The order is fixed because it must be. Explanation without a stable object is impossible. The Milky Way's shared naming across human societies reflects this universal cognitive order. In this sense, the Milky Way is less a story about shared mythology than about shared perception. It demonstrates that when humans look at the same sky with the same eyes, they tend to carve it up in similar ways. Differences arise in interpretation and meaning, but the first act is always recognition. The luminous band appears. It is seen. It is named. Everything else follows.